Good morning, good afternoon, and good evening. It's a great pleasure to welcome you here today on behalf of IPCP, the International Panel on Chemical Pollution. The IPCP is an international network of academic scientists working on various aspects of chemical pollution. And we're hosting this webinar series today. The webinar series is part of a project of PAPs in Plastics, which is part of GEF-funded effort on capacity building and monitoring. And IPCP is very thankful to Dr. Roland Weber for his leadership on this project and to all the speakers and collaborators, as well as to Lisa Zvereva from University of Toronto for her assistance with the webinars. Today, we are beginning the third part of the webinar series on extraction and cleanup and analysis of PAPs in plastics. Previous sessions have been recorded and are available via IPCP website, and we'll share links throughout the session. I am very much looking forward to today's presentations, and I want to encourage you to put questions in the chat as you come up with them, and we will get to them during the Q&A portion of the webinar. Now I hand off things to Roland, who will walk you through today's agenda and introduce speakers. Thank you.
Yeah, thank you, Anna, for the kind introduction. Good day to everybody. Welcome to our third part of the webinar series. So today we go into detail of extraction of POPs in plastic and on the cleanup, a very important part in the monitoring. So here we have an expert from Fraunhofer Institute, Ludwig Gruber, who will introduce in the first part of today's webinar on some lessons learned to protect the analytical instrument, on different extraction methods of POPs in plastic. Then after the break, we will have experience for capacity building on extracting and analyzing POPs in plastic for developing countries. Here from Dr. Omotayo Sindiku from Nigeria. And then we will have three presentations on some specifics. First on extracting PFAS, even if they are kind of covalently bond in side chain fluoropolymers. So that's a specific extraction question. And this will be presented from Professor Huang from Tsinghua University. And the last two presentations, here we will have Dr. Nudjarin Ramungul from MTEC Institute in Thailand. So she will introduce to the screening methods of brominated flame retardants in electronic waste plastic without extraction, with the FTIR method, and also screening on chlorinated paraffins and other plasticizers in PVC without extraction here with the pyrolysis gas chromatograph mass spectrometer. Yes, we will. Please ask your questions. I think today we will then directly after the presentations look to your questions. And by this, we can start with the first presentation. And our first presenter is Ludwig Gruber from Fraunhofer Institute for Process Engineering and Packaging, Freising, Germany. So that's an institute who is specialized on packaging, including plastic packaging and migration of chemicals from plastic. So he is the head of the contaminant laboratory and has worked more than 20 years on contaminants in plastic, very much on food packaging, which is the major area of the institute, but also the institute is working since more than 20 years on e-waste plastic and extracting and separating polluting from e-waste plastic. So he has a quite broad knowledge. So the first presentation is on some lessons learned to protect the analytical instrument when analyzing POPs in plastic. we thought that this topic is very important for all laboratories which plan to start analyzing plastic, but in particular also for developing countries where it's so important, let's say, not to have breakdowns of the instruments, because repairing instruments in developing countries can be a big challenge or up to a nightmare. So thank you, Ludwig, for your insight in the challenges with contaminated instruments. And please, the floor is yours.
I want to introduce myself a bit more in detail, because it's important to understand that the lessons learned to protect an analytical instrument is not only important for beginners. To be honest, we started some 32 years ago with analyzing dioxins and plastic materials, and it's not only a beginner's problem that you have to protect your instrument. It's also a huge problem for really experienced labs. Shortly, the Fraunhofer IVV is part of the Fraunhofer Society, and we have a number of business fields, and as Roland mentioned, we have experience in food packaging and also focus on recycling and environment. Our analysis laboratory exists since mid-90s, or let's say 1991, and we have also a department for process development, polymer recycling, and this is a spin-off of our working group. So the people from this department were former members of our working group. So we have a good cooperation with the people there. And this process development and polymer recycling department works on plastic recovery processes for WEEE, ELV, and also building waste. Our laboratories are accredited since 1996, and to get an impression, we own around about 35 mass specs and 50 GCs and around about 20 HBCDs. So it's really, I think, a good instrumentation situation at the Fraunhofer IVV. If we go to the process steps involved in our product development department, we mainly focus on mechanical recycling and chemical recycling, but the main process where we're working with is dissolution, the solvent-based purification of polymers. So some might know the Creosote process, but we have also developed other processes of plastics recycling. And Fraunhofer IVV was also the main institution who made it possible to have a closed loop recycling of PET bottles. So this is one of our important steps in the last decades. It doesn't work. Okay. We worked on a number of European projects. You see, or might see, that we handle all types of plastics and also different sources. So we talk about ABS, PC, ABS. We talk about polystyrene, expanded polystyrene, soft PVC. We talk about polyolefins and so on. So it's a wide range of plastics, and in your work, you will notice that it's really a very wide range of possible matrices which have to be analyzed, and it's completely clear that plastic itself is not one matrix. It's complex. It's very complex, and it might lead to problems if you underestimate the variance of your matrix. If we talk about analytical instrumentation, we use GC single quads for PBDEs, technical PCBs, phthalates, PAHs, and a wide range of other substances. We use LC triple quad for bisphenol A, nonylphenols, or perfluorinated substances. We have also some LC-GC couplings. We have also a high-resolution mass spec for dioxin and halogenated anisotropes, also for PBDEs. If we want to detect very low levels, we use XRF, X-ray fluorescence spectrometry, for elemental analysis, and we have a huge bunch of other instrumentation. So if I tell you something, it's not the fairy tale from people who are not experienced with analytics. If I'm telling you, since you can assume that we are really an experienced laboratory, and if I describe problems, then you can also assume that the problems happened at our institute either. If you talk about the analytes, we are analyzing, it's a huge bunch of substances, but for POPs, we analyze dioxins, PCP, pentachlorophenol, dioxin-like PCBs, halogenated phenols and anisols. It's more the classical analysis on the high resolution mass spec. Then we analyze plastic additives like UV and thermal stabilizers, antioxidants, and so on, as well as the derivatives. We analyze PBDEs and other brominated flame retardants. We analyze plasticizers like phthalates, addipates, and others. We analyze perfluorinated substances as well as the precursors. We analyze volatile organic chlorine, bromine, and chlorine, and have also developed our own detector for this purpose. And we analyze also phosphorus-based flame retardants, which are more likely to be analyzed with LCMS. And to be honest, the mixed plastic matrix, which I'm talking about today, is really a challenge, and it's a bit complicated to be prepared for analyzing mixed plastics. In general, in Europe, we have a situation that there's an EU action plan for a circular economy, which focuses on plastic materials. But to be honest, there's also an issue of safety and thus the need for analysis. So it's a bit contradicting. On the one hand, you want to reach this circular economy, but on the other hand, you will enhance the safety of your products, and this is sometimes a little bit contradicting. If we talk about closed loop recycling with a defined matrix, this is somewhat easy to handle. PET recycling is such a success story, but that's not the point where I'm talking about. That performing analysis in different matrices and a mixed and unknown matrix is a challenge and needs a lot of experience in planning. Otherwise, you can easily block your laboratory. We, as an experienced POPs lab, had to learn our lessons too. So it's not a problem of the beginner, it's a general problem. So if I have to mention that we talk about analysis of extracts. There are some screening methods which are fairly simple, so you can use X-ray fluorescence for your elemental composition, and it's not an issue. You can also perform headspace GCMS, which is a very important tool for safety and aroma analysis, and it's also not an issue because it's very simple to handle. But if we are talking about POPs, most of these substances are not available for headspace GCMS. So we have to change to liquid injection GCMS, and we have to change to HPLC. And then the matrix is a challenge. And the further thing is the analytes are a further challenge. We are talking about, let's say, we are analyzing some 200 substances at the moment at our institute. A recent study by UNEP has found that 13,000 chemicals are associated with plastics and plastic production, and 3,200 substances are of potential concern due to the hazardous properties. It is part of this webinar to strengthen the scientific knowledge and analytical capacity. And keep in mind, we're talking about 3,200 substances are of potential concern, but we have also derivatives from these substances. We are not talking about 3,200 substances, we're talking about 3,200 substances and their derivatives. So it's not such easy. And performing analysis of such a wide range of chemicals, and already mentioned variable matrix, this is a huge challenge. Yeah, we have different sources of plastic waste, and this has also influenced to the development of methods. So the material streams of interest are, for example, closed loops for food contact materials. That's relatively easy because you have the possibility to develop your individual methods. Also, almost simple source for plastic waste are textiles. So the only problem is if you talk about used textiles, you have a lot of grime and debris, so you have to handle the contamination, but it's not really a problem. But we have some sources with less predictable composition, mixed household plastics, electronic waste and scrap, automobile scrap, and building and construction waste. So we have the problem, you need a complex planning, sorry for that, not planning, planning and a method adoption. So let's talk about possible analytical problems. There's a number of them. First of all, some additives and impurities are present in very variable concentrations. So if you talk about soft PVC, you might end up with 70% of plasticizers. And if your method foresees a final volume of 1 milliliter, you will end up in your substances diluted in your plasticizer. And this will not work. So keep in mind that even if you do not analyzing for some additives and impurities present in very high concentrations. And last but not least, the oligomers and polymers can be dissolved in your extracts, and they will and can destroy or at least contaminate the GC column and the ion source of your mass spectrometer. So you will end up in non-functioning instruments. Even plasticizers, I already mentioned it, are present in such amounts that they will issue solubility problems. So if you have no analytical problems, you end up with solubility problems. And monomers can polymerize during sample storage, or which happens especially for butadiene copolymers, can also polymerize in the liner or somewhere else in your instrumentation. The samples are not clean. There might be dirt, debris, and dust which disturbs the analyzers. And last but not least, some of the investigated compounds are ubiquitous. So have a look on blanks. I can tell this because we are a lab which is specialized in the trace analysis of phthalates in plastic materials and also in beverages, and we make often the experience that labs tell people that we have a lot of phthalates, for example, diacyl hexyl phthalate, in your packaging or in your food or in your beverage, and it might be the case, but in, let's say, 80%, the people have not, we are not aware about blank issues. If you buy normally normal solvents, you will find some amounts of DHP in your solvent. And if you use it during analysis, you will obviously find DHP in your samples, but it's not, the samples are not the source of the DHP. So blanks is really an issue. And for some substances like the PBDEs, they might degrade during GC analysis, so you are forced to use short columns to avoid this. So, how to start? Start with a proper planning. Try to collect as much information about your samples to be able to perform an appropriate sample prep and extraction as well as cleanup. So one of the steps is getting representative samples, and this has to be planned in advance. But that's not the only point. You should use, if it's available, you use XRF, X-ray fluorescence spectrometry to collect first information on the sample. So if you are looking for brominated flame retardants, you should look for bromine. And the further indicator elements, e.g. chlorine, etc. If you want to perform an extraction step, don't start with the extraction step. Perform simple tests with solvents. What's about the solubility of your plastic material to understand your samples. And this makes it really necessary that you have a good communication between the coordinators of the project with the laboratory. You have to talk with each other, and otherwise you will end up in blocked instruments. That's an experience which is really important. For our lab, it's a must that we have a good communication between the coordinators of the project with the people in the laboratory. And without this communication, you will not be able to perform proper analysis. The first thing is keep extraction processes as simple as possible. Every single additional step will lead to additional problems. And I will explain it later. You can use XRF to test the extraction efficiency for some substances, for example, for the brominated flame retardants. You can perform repetitive extractions to understand if your extraction you have reached a full extraction. Next point. Don't use milling and grinding as sample preparation unless it's unavoidable. Try to use cutting instead. Milled samples will lead to more amount of matrix in your extract and thus lead to analytical problems. I don't think I said I can't. I have to repeat this again and again and again and again, because normally you have some coordinators which are not aware of the situation in the laboratory, and they have learned some basic analysis at the university, and they have learned that it's necessary to mill and grind samples, and this is not a good idea for plastic materials. First of all, if you mill and grind your samples, you have the problem of contamination, and also the loss of volatile substances is very likely. Furthermore, if you have some antioxidants, for example, if you grind it, normally you have partially high temperature during grinding, and this may lead to the formation of derivatives, for example. But the main problem is really the matrix. If you grind it in a very fine way, you will end up in a lot of dissolved polymer in your extract, and this will unavoidably lead to analytical problems. If milling is unavoidable, dry milling is recommended, but this will not solve the problem of representative sampling due to the limited amounts. So if you use a dry mill, you can produce some gram of your material, but it's not a good idea to mill some, let's say, 1 kilogram of samples. If you use the cryo mills, you will need some weeks to be finished with your kilogram of samples. It's a good idea to use processes which are already available. In our case, that's the case because we develop some cleaning steps, some technical steps for polymers. We also developed some cutting tools. So, for example, you see here an example for a preform cutter, which makes preforms cut it into small pieces, and this was developed at our own institute. It's not a commercial product. If you have to do a cleanup, one very simple step is the addition of silica sulfuric acid for dirty samples, or the use of small silica columns for cleanup samples with high matrix content. One possibility is also to store the samples in the fridge for some time. You will find some polymers in your sample, and this might have to avoid it to inject it to the GC. It's important to keep in mind that for some substances you need short columns, and it's also important to use high temperature columns. Plastic samples normally tend to be not the easiest samples, and you need some temperature to remove some substances from your instrumentation. One really important step: start with measurements. Means starting with diluted samples. It's really an important precaution. And the second, use splitless injection. Don't use split injection with undiluted samples. I can explain you why. Why not to use split injection? I will cite Wikipedia for a moment. What you see here is a picture of a splitless injector, and there's some explanation. Most of vaporized sample goes to split vent. Yes, but your oligomers and polymers in your sample will not vaporize at all and will not go to the split vent. They will stay at best in the liner. So there's a difference of injecting a sample with a split of 1 to 50, or to injecting a sample with in splitless mode, which is diluted 1 to 50. There's a factor of 50 between the amount of oligomers and polymers in your liner, and this is really important. And I've seen it often that people think, yeah, I have a split of 1 to 50. 50% of my sample will exit to the split, but this is not the case. So be careful. It's really important to understand this step. So it's also important to test some stability issues. Your injector temperature has to be high enough for the analytes, and you need also a kind of temperature which brings the substances over the transfer line, but you're only 10 degrees away from some thermal processes which destroy your samples, for example, for the PBDEs, and even changing the instrumentation. So it's not the same if you have a temperature of 300 degrees on an adjuvant GC or a thermal GC. It's different. So you have to test it by your own, or you have to ask people who own the same instrumentation. Yes, and to make performance tests and make blank checks. This is really important during the measurement campaign. And last but not least, if you perform a measurement campaign, reduce the oven temperature when there are no measurements, because otherwise you have a better transport of disturbing substances, high non-volatile substances in your system. Okay. To avoid some analytical problems, one of the most important things is to use the adequate solvent. So you have not too fine samples and you need an adequate solvent. Generally speaking, liquid extraction in chemistry is a separation process consisting of the separation of substances from a solid matrix. It's important, separation of substances from a solid matrix. It's not dissolving the matrix, at least if it's possible to avoid it. If you dissolve your matrix, you need a participation step or precipitation step. So it's sorry, it's wrong. And it sounds obvious, but it is important to note it's not a good idea to inject dissolved matrix polymer into a GC system. And it's really a very, very, very bad idea. And you should do everything to avoid this. And also important, your analyte, so the substance you are looking for must be soluble in your solvent. So the choice of a solvent is really important. Let's talk about factors influencing the efficiency of solvent extraction. It's clear that time and temperature are an issue. The solubility of the analytes in sample and solvent. And keep in mind that you have up to 70% additive concentration in the polymers, so it's really important. So another thing is, it's a partition. Extraction is always a partition. So the partition coefficient between solvent and polymer is important, and the diffusion coefficient in the polymer, because, as I mentioned, we don't want to grind and mill the samples. So you need to have an understanding of the diffusion of substances in the polymer. You might have swelling or dissolving effects, and it's important to note that the pH is also an important factor. And if you are looking for diffusion coefficients, so it's quite different for different polymers. If you talk about polypropylene or in general polyolefins, we have high diffusion coefficients. And if you look at PET, for example, it's the opposite. So you see, it depends on the temperature, it depends on the the diffusion coefficient depends on the temperature, and it depends on the kind of polymer. So the necessary extraction time for an optimal extraction may vary. And as a rule of thumb, grinding or milling is not necessary at all for polyolefins. And for GPPS, which means general purpose polystyrene, this is likely to be dissolved in most of the extracts solvents we use. If you want to go into detail for migration prediction, we were forced to develop models for diffusion coefficients. So you can use this work for migration also to predict the behavior of substances within your plastic material and the need of preparing or handling the samples. And it's also important, it's not only the plastic which is important, it's also the analyte you're looking for. So some POPs have different log KOW. Log KOW is the octanol water partition coefficient. It's more or less temperature independent. It's a bit dependent, but to a very low degree. So BFRs, brominated flame retardants like PBDEs, are absorbed to organic matter within the environment. And this is understandable if you look at the KOW. It ranges from 5.96 to 9.16. This is data from ECHA, the European Chemicals Authority. And you look to decabromodiphenyl ethane, which is also a common brominated flame retardant. It has a log KOW of 3.55, so it's not as lipophilic. If you talk about organophosphates, the so-called PFR, like TCPP or TCEP, we talk about the log KOW of 1.44 and 4.0 so we are in a lower range of partitioning coefficients, and this will result also in to choose not hexane as an extractant or as a solvent for extraction. You have to use, for example, acetonitrile, and you have to go to the LC instruments. And if you talk about the polyfluorinated substances, the PFAS, which are ionic, you will not use hexane. You will use something like methanol. So the values of the log KOV will give us also a hint to choose the right extraction solvents. If we talk about polybrominated diphenyl ethers, you will see that we talk about a number of them. And as I mentioned, the BDE 209 is the one which is very sensitive to the length of the chromatographic column. So it's really important to keep this in mind. And we talk about some 100 or more substances, and it's always necessary to have a look at the appropriate literature. Why I mentioned the PBDEs, because the next examples are focus on the extraction of PBDEs. So BDE 209 has around about exactly 10 bromines, and if you keep in mind that the molecular weight of bromine is 79 or 81 respectively, we are talking about masses which are higher than 800, obviously. So you would expect that extraction might be problematic, but to be honest, it's not problematic at all. If you talk about polyolefins, you can assume that they are not, without temperature, you won't be able to dilute polyolefins. And it's also not a good idea to dissolve it, because if the temperature goes back to 20 degrees, normally you will find your polyolefins as a wax within your liquid sample, and this is not very helpful. Let's talk about possible extraction ways. But let's say, do we have any questions to the subject of protecting your instrument?
One comment I have, or also question, is about this KOW for the dechloromodiphenylethan. So you said that from ECHA or from the dossier, it is 3.55. This would mean nearly 6 orders of magnitude lower compared to decabromodiphenyl ether. I remember that Martin Scheringer gave one time a presentation about submitted data in dossiers, and I think he used here this as one example where he questioned if these data are correct. Because I mean, also from your experience, when you compare handling decabromodiphenylethan and decabromodiphenyl ether, do you feel that there is a big difference, or do they rather feel the same? Yeah. So probably 3.55 is not correct.
Yeah. We had a short story at our lab. So we made some experiments with acetonitrile and also some extractions with other solvents. And the funny thing was that at one point we noticed we were not looking for the assay. And we saw it. So we repeated the whole thing with toluene as a solvent, and under some special conditions. So it was a mixture. And the next point was we found the BDE 209, but we did not find the decabromodiphenyl assay. Not at all. And only a slight change in or an addition of some solvent mixture leaded to a situation where we were able to see it, and so it's really complicated. Yes, if you look at the chemical formula, it seems almost to be the same. Yes, but it's not. It's completely different in the solution behavior, and you have to really test if you will be able to see it. So it depends a little bit on. Keep in mind that you have also a situation where an extraction is a partition between the plastic material and the solvent. Under some circumstances, log KOV leads to a really bad extraction. I know that this might sound complicated. It's not in a way complicated if you are able to perform tests with XRF, with X-ray fluorescence. You can test your extraction efficiency, and you will see if you are able to extract it or not to extract it. Otherwise, if you have no XRF instrumentation, you have to choose a number of solvents. For example, you can use mixtures. So to be honest, it's not the intention of this talk to explain everything and have ideas for everything, but you can vary your solvents. If you have a knowledge about your analyte and you know the PBDEs and you know that the dechloromethylphenylethane is also a very common brominated flame retardant, and you want to look for it, then you have to modify your extraction steps in a way not to dissolve your matrix, and you in a way to completely extract your bromine. There's a caveat. Sometimes you have also brominated polymers. So it's not always such easy, but I think for most plastic materials, except for foams, the use of brominated polymers is not such common. So you can expect what you will observe, but you need some experience. And back again, the problem is if you have some completely undefined mixture of plastic materials, you might run into problem. And this is what I wanted to explain to you. You need really a good planning of your analysis, and there's not one way to do these things.
So therefore you will give now, let's say, 2 more presentations on different kind of extractions. But I have one more question about the use of guiding columns, to protect your GC column. Do you have an opinion on that, or how is Fraunhofer Institute doing this?
In different, we have not a clear opinion on it. For our high resolution mass spec, where we have only one at the moment, we use pre-columns with a broader diameter. This gives you also some benefit for the chromatography and also protects your column. But there's one disadvantage. You have to couple these 2 columns with different diameter. And you can use glass connectors, or you can use some Restec or SGE provides some metal connectors, and they work. But sometimes if you have this high temperatures and this change of temperature during the measurement, it might happen that these connectors fail, because you heat up to 340 degrees and go back and so forth. And if you're running day and night, there's some likelihood of running into problems. And due to the fact that you have a very short column, it's also a problem for the MS, because how to explain it? The amount of gas or oxygen passing to the MS might be high, and sometime we had a situation where the instrument didn't stop because there was not enough gas flow to stop the instrument, but it worked furthermore, and it was too much oxygen for the instrument. So it's we use it, and I recommend it for some circumstances and some very difficult matrices, for example ABS. So you have a problem with mesobutadiene copolymer, which might form polymers within your GC, or even better on the hot surfaces of the iron source of the MS. And cleaning this might be a complete nightmare. And then pre-column is a very good idea. But you have some disadvantages, but it depends on what kind of matrix you're working, and the instruments are more, we protect our more sophisticated instruments. We do not protect our semi-quad mass specs. I don't know. It's really hard to decide. It has a lot of advantages, but it has also some disadvantages.
Good. No, thanks. Good. There was one question from Mumuai about the presentations, but yes, I think you will give the presentations to IPCP, and we will put the PDFs in the web. Yeah. So this will come together with the recordings. You will find presentations later on the IPCP web. Good, Ludwig. Then you can come to your methods on extracting the additives from plastics.
Yeah. So the analyte which I'm talking about is are the PBDEs. Yes, a completely simple approach for polyolefins. Short. Is it already? Can you see the presentation at the moment?
We have the PBDE slide in front of us.
Yeah, it's okay.
Now an easy and for most cases appropriate extraction.
Yeah.
Okay.
So it sounds unbelievable, but it's a very simple approach. You can do a static extraction by using 0.5 to 1 gram of the samples and putting it in a glass ampoule, putting 5 to 50 milliliters toluene onto the sample and put it in a laboratory shaker or an oven at constant temperature over a period of 24 hours, and ta-ta. You will notice that you have some, if you talk about foams, you will have some chill, or if you have some polyolefins, you will find not much change to your polymer. And you put 1 milliliter of the supernatant, subject it to PTFE syringe filter, and can analyze it. It's perfect. The problem is you should be sure that nothing has been dissolved. And this is not the case for pure polyolefin samples. It is also not the case for pure polystyrene samples, but it might be the case for mixed household plastics. So this method might work, but it will not work in every case. So it depends on what kind of samples you are using. So it's really completely easy. It's not sophisticated at all. And to show you some example for the results of some testings we performed, there are some from the European Union Bureau of Reference Materials, there are two types of reference materials, which are LDPE and PP, both polyolefins. And there we can perform an extraction without filtering. So we looked at the following PBDEs and polybiphenyls. And yeah, we had a very simple analytical method with temperatures going to 340 degrees, a Restec column which is similar to a DB5. And we performed some measurements, and to be honest, it's not spectacular. We had some typical mass fragments, and you see the results. We worked with an internal standard, isotope level standard with C13, and it's absolutely clear. So there's no problem of analyzing it. And if you have a look on the results, the replicates, it looks fine. There's a deviation from the certified value of 0.3% and uncertainty of 11%. And to be honest, it looks really fine. If you have a look on the replicates, you will notice that the last replicate is a little bit lower than the others. We don't know why. But to be honest, it looks as it should. So let's repeat. We only put the sample in a vial, we put some toluene on it, we do nothing except waiting 1 day for at 60 degrees, and we injected the samples and it works, and it doesn't destroy the instrument at all. It works very well. So you might think it looks not realistic, yeah. If you think about validation, I talked about validation. What can you do? You can have a look at the extracted material, and we used the spectroxepos spectrometer for this measurement, and yeah, we analyzed the sample before extraction and after extraction, and we saw a bromine content of less than 1% in both sample materials. So the extraction was complete. So I would say it's completely proven that we are talking about correct results. It's a reference material where we know the concentration of our PBDEs and PBBs. We found for all of them so right concentration with a range of, let's say, within 10% and with a validated measurement uncertainty of about 20%. So it could be so simple. And let me ask let's answer what could we do if we are not in the possession of an XRF instrument. We can perform more extractions. So you repeat the extraction, measure it. You have to add additional internal standards, or you have to think about the quantification process, because the isotope level standards are also extracted, so you can't use it in the second extraction without some approach of quantification. But you can perform, let's say, 2 additional extraction steps and have a look on the values of your PBDE, and you should see also almost no PBDEs in the second static extraction. Keep in mind that some remains of the solvent of the first static extraction will remain on the samples or will migrate into the plastic material, so it's always a partition, so it will not work perfectly up to 100%. The 99% can be explained also with the amount which we gave, the amount of toluene we used 0.5 gram to 50 milliliters of toluene. So we used more than normal amounts of toluene. But we knew the expected concentration, and you can adapt your ratio of matrix to solvent, and this might help you to come to a better extraction efficiency. Just a moment. Yeah, but it's not always such easy. So in a lot of situations, you are not quite sure if you are able to provide a complete extraction. As I mentioned, the diffusion coefficient within polyolefins leads to higher transportation rate and extraction efficiency than for other polymers. For foams, for polystyrene foams, you have not to discuss diffusion rate, because in this case most of the plastic materials are dissolved or swollen, so it's not an issue. But you have also other materials, and if you want to dissolve some plastic materials, toluene is not the best choice. One of the possible solvents is tetrahydrofuran, where you can dissolve a lot of plastic materials, and then you can precipitate the polymer with hexane or ethanol. You have to wait some time, filter it. You can dilute the solution with cyclohexane and analyze it on the GCMS. Yeah. It's sometimes important to pass it to a PTFE syringe filter, but to be honest, you have to be careful. Yes, you have to use the right filter, or if you can, let's say, for example, example from our lab, we used for polyfluorinated substances, we used the appropriate filter, and you can be sure that we did not use the PTFE filter, but we used some nylon filters, and we got the repeatability in the lab was really bad. And after a while, we tried to find out why, and noticed that the repeatability was bad after the syringe filter. And we noticed that the nylon filter was not appropriate for PFAS. Yeah, you can't use the PTFE filters either because it's Teflon, so it's a fluorinated compound with some likelihood of containing PFAS. So we ended up in using CME filters, which are not allowed for this type of filtration, but the filters work. And you have always to test things. Yes, it's not such easy like an SOP, which is for one very clearly defined matrix. And if you talk about mixed plastic waste analysis, you have always to think about what could be a good idea to do and what could be a not so good idea. Okay. Here you see the dissolve and precipitate steps in photographs, and the last picture shows you the solution after, let's say, some hours. So in this case, you will not be able to inject it to your GC. You have to use a syringe filter to remove your plastic particles. And we just talked about our toluene extraction, our static extraction. There's a simple step. If you will notice that using toluene leads to dissolution of some amount of polymer, simply takes a static extraction solution with toluene and use 1 milliliter of your toluene extract and add 5 milliliters of hexane. This will lead to precipitation also. And after some hours, an aliquot of 1 milliliter of this 6 milliliters can be used to the analysis on the GCMS. So it's quite simple, but the methods have to be adapted to your matrix, and they have to be adapted to your POPs, which should be analyzed. It's not always that simple, yes. Let's mention some additional steps we use. We use column cleanup sometimes. We use sulfuric acid silica. So the simple addition of sulfuric acid silica might help you if you have extremely dirty samples. So some organic substances, fat or something like that, can be destroyed with sulfuric acid. And it can be destroyed by adding it to the into the vials. But you have to keep in mind that not every single POP is really stable during the presence of sulfuric acid. So keep in mind that some additives, for example, will be destroyed by sulfuric acid. It will not only destroy your fat and fatty acids, it will also destroy, for example, UV stabilizers. So if you talk about toluene, you would destroy your substances. sometimes you are obliged to use size exclusion chromatography. This is additional instrumentations. Some problems cannot be solved without size exclusion chromatography, and it's also possible for in some situations it might help to add some silica to the extract. I cannot explain every single possible step. There are a lot of steps. If we develop or if we work together with partner labs, we try to explain it in practice. We want to provide the lab personnel some ideas what can be done, but it needs really communication between the project coordinators, laboratory heads, and the people in the laboratory to find out the necessary steps. Otherwise, you can really destroy your instrument. And to be honest, we had the situations that we worked for months on some instruments to get it back running, and we lost one GC-ECD and one Agilent GC. We were not able to restore it to function. So it's not only a problem of beginners, it's a problem of every single lab which works with the substances. You have to be careful, very careful, and you have to take care also for blanks and stability. Okay, the presentation will be continued next this Tuesday, but I want to go back to one aspect which might be interesting, or I don't have some presentation. So I told you that it's important not to be too aggressive to your sample. That's in short word or in one sentence the message I want to give to you. But there are some situations where this is not possible. So you have to adapt really your methods to the situation. If you talk about plastic samples which contain carbon black, which acts like active charcoal, you might be in a completely different situation. If you might know that we have some rubber recycling from automotive tires. This is not plastic in usual words, but it's rubber, and you have a presence of carbon black. This carbon black might act as a it will not give you a chance to extract it without brutal means. Then you can use really harsh conditions. For example, we use accelerated solvent extraction at 100 degrees and pressure, and we try to extract it under as harsh conditions as possible. So if I'm talking about smooth extraction. It's it should be the case, but under some circumstances you are in a situation where you are not able to use this smooth extraction method. So it's always the case that you have to think about the effectivity and the the appropriate means. So I think this is the main topic or the main goal which I wanted to transport to you. Plastics, mixed plastics are really a complex matrix. You need a lot of thinking before performing the analysis. And so in most of the cases, there are simple ways of solving the problem and not dissolving the matrix. So I hope it was possible for me to provide you with some insights in our experience with the analysis of plastic materials. And I want to stop now, and I think we have some time for discussion.
Yeah. Thanks, Ludwig. So this was, I think, your first method you wanted to introduce, right? Because you will have the second part where you go to the dissolution method, right?
Not today. This dissolution was in dissolvent precipitation.
Okay, good. So therefore, you gave the full overview. Yeah. And maybe one question from my side. You mentioned, because Ludwig is also participating in our project, on our UNEP GMP project on the plastic pellets. And you told me there on your experience, I mean, how you do it practically, and that you started with one method and then you changed. Maybe that's a useful practical example which you could, let's say, tell. I mean, how when you get now, let's say you got samples from Nigeria, from Thailand, from different countries, yeah, and then how you practically have done it and have started it. Yeah.
So if we get some really unknown samples, it's important to have some insight on the materials. And we know the situation in Germany very well, I think, because we are involved in so many projects. But all over the world, we have different situations with the plastic materials used. So it might completely different to our experience here in Germany and here in Europe. One thing which has happened before was that some of the materials were tested for bromine and also chlorine. So you have some information about chlorine. If there's no presence of chlorine, you can assume that you have a low amount of PVC. PVC might be really problematic because if you have 70% plasticizer in it, it gives you a solubility problem. Soft PVC, for example, has up to 50 or 70% plasticizer. So we have some information about the bromine content. We have some information about the chlorine content. We can use also some elements as indicate the elements. For example, tin, which is a thermostabilizer for PVC, or some typical elements. And the first step is normally that we use some solvents. We use hexane, we use toluene, we use THF, tetrahydrofuran, and SNO and have a look what happened. Take a small amount of the sample. It's all, we do not use really representative amounts. It's a bit complicated if the samples are not made, but we try to use not only one piece and put it into the solvent and have a look on the behavior. Normally, you will see some solution or dissolving processes, and if you see it, you have to keep in mind what kind of solvent it was, and if, for example, toluene does not show dissolving process, the easiest approach is to do a simple static extraction. Then you put it for, let's say, 60 degrees on the shaker, and sometimes you will be a bit surprised that after using temperature you will run into a dissolution of your sample. You have to really keep in mind the situation with before and after the shaking process, and if it looks fine, we dissolve it again a factor of 1 to 10 and inject it. We dissolve it in toluene, 1 milliliter plus 9 milliliters toluene, factor of 1 to 10, and inject it. It should not give problems. If we are not quite sure what has happened, we would use hexane instead of the toluene. This is, let's say, not perfect, but working precipitation step. So this will lead to a precipitation of the polymer matrix, which was dissolved normally.
This mean you first you had dissolved it in toluene, and then you add some hexane there. Yeah,
and this works also as a precipitation step. It works not as well as if you, for example, if you use THF, tetrahydrofuran, which is a very polar solvent, and you put some hexane in it. It works different. Toluene and hexane are very nearby, so the precipitation step works technically speaking not as perfect, but it will lead to a precipitation of the polymer. And if you, it's on a normal circumstance, it's finer, the structure is finer, and it's not what you want in a technical process, but for analysis it works well enough. And then you have changed from a simple static extraction to a not completely perfect but working precipitation step. So and for the samples, e.g. from Nigeria, it turned out that it's necessary to do so. We do not understand why it's necessary, but we have some better soluble polymers in this waste samples. Maybe we'll understand it at the end of the project, but at the moment it's a simple fact that we have some amount of soluble plastic waste within the material, and it disturbs our measurements. And the next step is adapted to the analytes. You can put, as I mentioned, silica into the solvent, or to have a better sedimentation. But the problem is There is some partition between the what do we analyze in the UV328? Yeah, it's a UV328. Then we lose some intensity of the signal. So in this case, we cannot add the silica. And under some circumstances, if you're talking about very dirty samples, where we have some fats or something like that, we use sulfuric acid silica and put it into the solution. But in this case, you observe a complete destruction of the UV328. So you have always to be careful with some easy steps. You have to counter check it if they are not influencing your analytes. Yeah? So if you're talking about the PBDEs, they are completely stable against sulfuric acid. But some of these newer pops, and especially if you talk about UV stabilizers, antioxidants, or something like that, they are produced to react and might react with under some circumstances. So you have to be careful with your additional steps. And if you modify something, you have to counter check it by the appropriate analytical means.
The methods, I mean, which you presented here, do you have also some publications, I mean, where in addition to the presentation, where people might check, or is there somewhere, let's say, guiding materials to this kind of extraction of plastics and precipitation of polymers and so on?
Yeah, we are just developing, in addition to the unit guidance, some material, but it's not available at the moment. We have published some things. We have published, for example, one method for HBCD in foams, one fast method in 2015 we have a change from HBCD as a bromine flame retardant to polybrominated flame retardants. Polymeric flame brominated polymeric flame retardants. And in this context, we also described our method for the PBDEs, and there are some tricks also for the solubility. We played with the solubility of things, so we can provide a number of publications, but it's not. We had a whole bunch of methods appropriate for special projects, and I think we can provide this information within the next 2 months or so.
You mean the manual? Yeah. I mean, maybe to the audience, we have at the moment a project in Ivory Coast on capacity building of a laboratory for measuring PBDE in electronic waste plastic and in end-of-life vehicles within a UNIDO, a World Resource Forum UNITAR project, where capacity for this kind of recycling of these materials is developed in the country, and at the same time also some laboratory capacity. And for that, yes, we are at the moment discussing if Fraunhofer Institute can develop such a manual for the project. But in this project, we also see, I mean, how important it is to take care of the equipment. Actually, we are more than 6 months behind. And the main reason is they have one instrument and this instrument is not working. Yeah. Some small things. One was helium, another was something with the mass spectrometer. But it is really these kind of hiccups in developing countries for the equipment that whole large projects might not move forward. So therefore, the first part of today's presentation of Dr. Gruber is of high importance when developing countries want to start this kind of analysis, because polymer matrix is much more risky for sure than water or soil. And therefore, Ludwig, I'm quite happy that you have explained here the nitty-gritty. Maybe if you like, you have mentioned your presentation where you let's say have published to distinguish hexabromocyclododecan and poly-FR in materials. If you have the publication, maybe you can check, and you could put the link in the chat. Yeah, maybe also for some other publications, if you like, you could put the links in the chat that participants can look it up, and I think that would be helpful and useful. We had and that this come later, fluorinated polymers. Do you have any experience with fluorinated polymers like PTFE and extraction of those materials?
Yes. But it's a very special topic. One of the problems is that you might be interested in some PFAS and also some fluorinated hydrocarbons. And the problem is that the PFAS can be only extracted with some methanol, and it works not very well. So you have to work with a high amount of solvent, and you have to perform SPE, which works well for the PFAS, but not as well for the fluorinated hydrocarbon. So we decided to use some Perch trap. So you have to divide it in the ionic and PFAS and divide it into the non-ionic perfluorinated substances. And the non-ionic substances are, we have developed a detector which is called EPET, where we can measure the fluorinated hydrocarbons very well. And also some volatile substances like the F2Hs, fluorotelomere alcohols, and also P. So not as ionic substances. So we try to avoid, in this case, use of solvents. So we try to use Perch and trap process, which is integrated to the GCMS, or so to the GCEPET, which is a fluorine sensitive detector like the AED. It's fluorinated plastics are not an easy target, and it's one of the points is that you use also surface induced fluorination, where you have very low amounts of fluorine compared to the amount of plastic, and but you have a high probability of formation possibility. So in this case, the precursor problem is one which is arising, yes, because it's a bit complicated. If you perform some, you can, to change the behavior of a polymer, you can add some fluorinated side chains to the surface. And this side chains are not always stable. So it's possible to have some F2H side chains, for example, and if you have geotextiles, for example, which see some UV light and some organic or biotic influence, you will end up in some PFAS at the end. So, for example, we had a funny experience in Germany with an airport, which has a testing site for the fire brigade, which where everything was new and everything was without fluorinated substances and everything was perfect. And for environmental reasons, they used surface water or rainwater for testing, and they found PFAS. And it was at the end, it turned out that some geotextiles, some polymer which was treated with some fluorinated surface, which was not extractable at all. But if you perform some oxidation processes with this textile, you will end up in PFAS. I don't know, it wasn't PFAS, it was P4. You end up in a PFAS substance. So fluorinated polymers and fluor-treated polymers are a very complex issue. And it's not always a simple extraction. We try to simplify things with so-called top assay.
For this, we will have a presentation in the second half from Professor Huang on this top assay and this side chain fluorinated polymers. Maybe one question to another important polymer you mentioned before. Your main headache is PVC. So when you have PVC in your samples, what is normally your strategy for the extraction and for the cleanup?
So the extraction itself is not problematic. The problem is the extract. We calculate the needed limits of detection. So we try to dissolve or dilute it and not to inject more than necessary. PVC, you have some organotin compounds, you have some plasticizers, you have some chlorine in, let's say, a form HCl, Cl2 or so. If it's so, under some circumstances, it's not a problem at all, but we try to avoid creating problems by using only diluted samples, and you can calculate it if you make some measurements. You have some experience how much do you need for the analysis? You can assume that the instrument like a single quad MS might work with, let's say, under plastics analysis conditions, 5 to 10 picogram is a sufficient amount of your analyte in most cases. So you can calculate how you can dilute your sample, and you should not start with samples which were evaporated nearly to dryness. You should start with diluted samples, and you will have a look at the reachable LODs, and then you decide to stop at a certain point. But it's not always the case that PVC is a problem. If you rigid PVC is mostly, in most cases, not really a problem,
No,
because
it's clear. It's the soft PVC, what you said with the plasticizers. Okay,
yeah.
and this you calculate over the what will be the final inject, and from there then you decide the amount of sample.
Okay, dann rufe ich bei Gelegenheit.
Welcome back to our second half of day 1 of part 3 of our webinar with the topic on extraction, cleanup and analysis of POPs in plastic. Our next presenter is Dr. Omotayo Sindiku from the late City University from Ibadan. Dr. Omotayo Sindiku measured brominated flame retardants already in her PhD 12 years ago. And at that time, we brought Dr. Sindiku to the Fraunhofer Institute, to the colleague of Dr. Gruber for capacity building. And so for this presentation, she will talk about her experience of capacity building on extracting and analyzing brominated POPs in plastics in Africa with a South-North cooperation. Yeah, please, Omotayo, over to you. You need to unmute. Yeah, no, you are unmuted, but we cannot hear you. Omotayo? Are you there? Hello?
Hear me now?
Now we can hear you.
Oh,
yeah.
You can hear me. So, hi everyone. I'm Omotayo Sindiku. Yes. So I welcome everybody to this IPCP Webinar Series on POPs in plastic and monitoring approach. Like Roland said, I will be talking on experience of capacity building on extracting and analyzing brominated POPs in plastics in Africa with a South-North cooperation. My presentation will be divided into 2. Capacity building in Sweden on part 1, and part 2 will be how PBDEs analysis was established in Nigeria. Introduction, we all know that PBDEs are one of the most widely used BFRs, and they have actually emerged as a contaminant of interest due to their widespread usage, environmental distribution, toxicity, and a whole lot of others. And there were even some congeners like tetra-BDE, penta-BDE were listed by the convention in 2009, and DECA was listed in 2017. So PBDEs, like we know, has been found in plastic and electronic waste, vehicles, buildings, and in particularly, they enter into the environment through indiscriminate disposal of end-of-life products. Plastic in electronic waste, we know, contains the largest share of PBDEs in the waste stream. Developing countries like Nigeria, Ghana, they have imported. We are still importing PBDEs containing products like vehicles, televisions, computers, and so on. And our major concern then was whether the levels of PBDEs and other BFRs increases in humans and the environment, and if they can cause toxic effects. So in Nigeria, we know that the major source of PBDEs are polymers of electronic waste, and most of our electronic waste are being imported from Europe, from Asia, North America, and Asia. There is no production of BFR in Nigeria and other African. We see that e-waste flow from the European Union and from China. Nigeria has been an hub for electronic waste imports from industrialized countries since the early 2000s, even way beyond that. Especially now in 2008, when China restricted e-waste imports. This is the situation we have in Nigeria. When electronic waste comes in, some are reused, some are refurbished, and the others, materials such as copper, while the largest share, which is a plastic, are being burnt. In 2010, a monitoring project for PBDEs in e-waste plastic was actually initiated by the Secretariat of Convention, by the Stockholm Convention, the Basel Convention Regional Center in Nigeria in Ibadan, which was headed then by Professor Oladele Oshibanjo, and it was financed by the Norwegian government. I and a colleague, Joshua Babayemi, was selected under the supervision of Professor Oshibanjo and Dr. Weber to conduct the research. So my PhD was on monitoring analysis of PBD, while Joshua, the other student, was on material and substance flow analysis. So for the capacity building of analysis of PBDs, I did a 3-month training at Fraunhofer Institute under Dr. Huang and Dr. Gruber. And in the second phase, I went for 6 months to University under Professor Tsinghua for the analysis of brominated dioxins and furans in e-waste plastic. One lesson I learned for people that want to do this type of money, for countries that want to involve in this type of monitoring program, is that the visa application to Europe takes longer time. So you need to consider the overall, you need to consider this in the overall planning. Then the second thing that was that stand as a stumbling block then was that our PhD, the second PhD students could not get a PhD grant to Vienna to visit Vienna University due to age restriction. So there are age restrictions to funding PhD students. The monitoring started and we collected 382 plastic of televisions and computers from 8 different locations in Ogun State and Lagos State, which are southwest Nigeria. While collecting, we noted the year of the region of importation, the year of production, and we label. And the first thing we did was we did a little bit of sample, we cut plastic samples from each of the samples into sizes about 100 mm to about 50 mm, and the samples were packaged and sent to Germany. 2 weeks later, I also went to Fraunhofer Institute in Germany for the research. So the first thing we did when I got there was we screened the plastic samples using energy dispersive X-ray fluorescence. This was done actually to separate the bromine plastics from non-bromine plastics. Then further analysis was carried out on the bromine positive plastic, which we had, and then I think we have 213 plastics. Extraction was done by dissolution and precipitation. We did cleanup and analysis by GC, done by dissolution and precipitation according to an established method by Schlummer in 2005 and 2007. We took I took 0.5 grams of the polymer sample into a well-labeled extraction glass vial. Add 5 ml of tetrahydrofuran. Then the glassware was placed on a shaker for 2 hours to ensure complete dissolution of the polymer sample. Then 2 to 12 ml of NXA was added stepwise with a rigorous shaking until we observe a good precipitate. Then the thing was allowed to stand on the mechanical shaker for another 15 minutes until we have a clear solution. And the glassware was allowed to stand for another 15 minutes, while the extract was then decanted into a well-cleaned and well-labeled collection bottle. this process was repeated thrice. And each time the extract was decanted into a glass bag. We have encountered a problem here because we have about 5% of the plastic that did not dissolve in tetrahydrofuran. So we use xylene to dissolve. Then for precipitation, we use acetone to precipitate them. After the extraction procedure, we clean up using an aliquot of the supernatant separated from the precipitated polymer was passed through a 20 ml syringe filter equipped with what, a 0.5 micrometer filter disc. Filtered sample was then diluted to about 100 folds of toluene and placed in a GC vial before chromatographic analysis. Results and discussion. This table shows the numbers of samples from each region, assembly or year of manufacture. We had samples from Europe, Asia, America. The largest amount of samples collected from Asia. A total of 158 samples was collected from Asia, while from Europe, from different countries in Europe, we collected about 150 samples. In 2010, only tetra-BDE to hepta-BDE were listed, which are PBDEs homologue of commercial penta-BDE and commercial octa-BDE, where production stopped in 2004. Therefore, in this study, only CRT produced between 1981 and 2006 were sampled, as shown even in the table. Then the results of the screening exercise by we screen for bromine, we screen for chlorine, phosphorus, and antimony. We find out that this enables us to kind of divide our samples into the one that contains higher concentration of bromine. Some contain, if we find plastic samples that contains we find out that 32.9% of the TB and 66.1% of the computer samples contain bromine at a level about 10,000 milligrams per kilogram. And we consider that as being flame retardant with BFR. So those ones were the one we consider in analysis or in the analysis of the PBDEs. We then went on. This is the chart showing the distribution of bromine contents of TBs. We find out that some samples contain commercial outer. The average, we have an average concentration of 1,280 milligrams for all the 382 samples, which was still above the maximum permissible level of 1,000 milligrams per kilogram. Therefore, these polymers cannot be used for recycling into electronics after removing the bromine containing casing. Then we also find some samples containing deca-BDE. 34 samples out of the 382 samples screened for BFR contains commercial deca with concentration ranges from 675 to 230 milligrams per kilogram, which actually corresponds to an average concentration of 3,850 milligrams for all the 382 polymers. Therefore, this average was found to be about 3 times above the RHS limit in average. Total, we also carried out an inventory of total BFR in Nigeria CRT plastic using the Stockholm Convention methodology and our measured and our average concentration of the octa-BDE. We find out from it the impact factor from our study, as you can see from the table, is 594. When we compare it to, we observed that it was higher than the Stockholm Convention of 242. And most of, if you look at it, even for EXA, 65 to 27, EPTA, 256 to 107. This was observed to be, the fact, it remains that this higher result was gotten because we sample old plastics that is from 1981 to 2006, while the one used in the Stockholm Convention inventory guide was electronic samples from an European electronic recycling plant, which contained majorly of the new electronic waste. So back in Nigeria, I transfer knowledge on PBDEs to Basel Convention Center, situated at University of Ibadan, where we established the first analytical capacity of PBDEs in Nigeria. So in establishing this, it was an opportunity for us because GRC laboratory was established by UNEDO at the Basel Convention Center. And that time, Federal Institute of Research, Industrial Research in Nigeria, the federal government got a new GC Sindiku. So we actually used that to start. But we faced some challenges along the way. Some of the challenges faced were lack of funds to purchase chemicals, another small equipment needed. We have power problem. Power is a big problem in Nigeria. We had a lack of support from the government, lack of equipment required for extraction. So we had to sit down and start and raise money by ourselves, the chemicals and every other things needed for further analysis. And while we were doing that, I trained some of my colleagues on PBDE analysis, and we test run for months before we started the work. After we established the analysis, we also selected research topic around dump sites or e-waste dump sites where plastics are being burned, openly burned in Nigeria. So we conducted and published several research on monitoring of PBD in milk, vegetables, and soil around dump sites and e-waste sites in Lagos and Abuja. These are some of our publications. However, there was no project opportunity to further analyze POPs in plastic in Nigeria. But now, a GEF project of plastic management is currently being developed. So our contribution to knowledge then was that we were able to contribute for the first time the much needed data on the types and levels of new listed brominated POPs in e-waste plastic. And the follow-up studies for soil, vegetables, egg, cow milk around dump sites in Nigeria. Data from our studies has actually been used by the Stockholm Convention to develop a methodological guidance, and it can also be used by policymakers for decision making vis-a-vis Nigeria's obligation as a party to Stockholm Convention on persistent organic pollutant. Similar capacity projects can also be or should also be conducted for other courses, and it will be beneficial for the whole continent. So in conclusion, monitoring capacities of PBDEs and other PFRE has been established by a North-South cooperation already between 2011 and 2013. The screening, extraction, cleanup at Fraunhofer Institute can also be applied in other developing countries. However, equipment, analytical standard, and in particular, research funding and projects is missing. Also, strategic development of research and monitoring capacity in developing countries also needed. There's also need for a better monitoring and proper management of electronic waste in Nigeria and other African countries, because we are still importing most of this electronic waste. And more research cooperation are needed to facilitate more research cooperation. Thank you for your attention and cooperation. This is the situation of things we have all over Nigeria. And I stop here.
Omotayo, you can say the last three sentences again, because there was fading of your voice.
Hello?
Yes.
Okay, there was fading of my voice. Hello?
Yes, no, yes. Now you are back. Yes, Omotayo. Thanks very much. I mean, thanks for this presentation. Yeah, but also, thanks for bringing the knowledge which you have learned then back to Nigeria, back to your country, and actually the last 10 years promoting PBD monitoring. But I think also you are doing heavy metal work on heavy metal and work on polyaromatic hydrocarbons. Yeah.
Yes.
One question about this kind of networking. Is there a kind of network in Nigeria, or are you aware of a network of African researchers on that topic, which let's say stimulate cooperation in research?
No, not that I know of. Most of us in Nigeria do independently because research in Nigeria or in Africa is generally expensive. So none. People are doing it separately, and most of those researches are not even published.
Yeah, this means also, I mean, your first PBDE standard you had to buy kind of from your own, from your own money, kind of.
Yes.
Yeah.
Yes.
So, do you have a recommendation for this kind of UN project? I mean, our project at that time was really small scale funding from Norway. Yeah, so that was a real small project with about $40,000. Where we could afford that you can come to Sweden and that you can come to Germany, go to conferences and so on. So there was not really, but when you look to this UNIDO project where they have purchased this equipment, do you have, let's say, a kind of wish from your side as a researcher from Africa, how, let's say, larger, or now when we come to this plastic project, how such projects would need to be framed that it help a researcher to grow and support their government?
Okay, yes, Roland, I think I have. You need to come in to give us a GCMS did not actually come with most of the things we needed. The consumer project like this, there should be a long time thing, not a short time thing. After the project, there should be like a follow-up or what you're doing, or maybe there should be a fund for further things or consumables that we needed. I think our one major problem then was that when we finished the project, there was no more fund, no more chemicals and everything. So for me, I would say the next one should be a long-term planning one. And the funding should be, there should be a, because for the GCMS, if we run into problem, we have to go and read online, read this and read that. We need people that, we need for instruments, we need maintenance. Maintenance has always been a problem in Nigeria. Like I remember when I was working in Umeo University with their high resolution GCMS, and I ran into problems. So I called Staffan. Staffan called, I think, Agilent agents, and they came and the problem was fixed. This type of thing we lack in Africa. I can't say for South Africa, but for Nigeria, we don't have that technical assistance and all sorts of things. We needed it. And any project they are embarking on should be a long-term thing. Yes, thank you.
Thank you, Omotayo. So our small pellet project is also, let's say, at the end of the global monitoring plan from UNEP, which was a more than 5 years project. And I know that UNEP is at the moment planning the next global monitoring program. And within this global monitoring program, UNEP is planning to do more capacity building and establishing laboratory capacity in developing countries. Yeah. Yes. So I mean, if you like a small homework, yeah, you could make a list and I could forward it to the next project coordinator. Yeah, as one input.
Do that.
Okay,
yes,
good.
I can do that. Yes.
Yeah.
Yes.
Yeah. Thanks. Thanks, Omotayo. Yeah. Okay, so you can stop sharing screen.
Okay, thank you.
Then we come to our next presentation and presenter. This is Professor Huang from the School of Environment at Tsinghua University. So the institute also hosts the Stockholm and the Basel Convention Regional Center for Asia and Pacific. And back in our webinar on 19th May, which is recorded, in my last talk about monitoring fluorinated POPs in plastic, I highlighted the importance of side chain fluorinated polymers. Because, for example, when you look for PFOS, we find that more than 70% of all PFOS in 2000, which was the main year of use, and where we have data, we see that PFOS has been used in side chain fluorinated polymers, and only less than 10 times or even 50 times has been used in firefighting foams. This means that these side chain fluoropolymers are really relevant as a PFOS reservoir, but also as a PFOA reservoir, and in current production for other PFAS. But they are covalently bond and therefore difficult to extract. This is what Dr. Gruber, let's say, mentioned when he said, yes, oh, the analysis of these fluorinated polymers is quite complicated. And one option is here the degradation of these side chain fluoropolymers. And Professor Huang has worked on a total oxidizable precursor, top assay, and developed an own top assay. So here, Professor Huang, the floor is yours, and your presentation on top assay, a tool to characterize PFAS in commercial textile finishing agents and AFFF surfactants, potentially containing side chain fluoropolymers with a small question mark. Yeah, so over to you.
Thanks very much, Dr. Weber. Yeah, thank you for your introduction. It's my great pleasure to talk something about our previous study. We use TOP assay as a tool to characterize some industrial formulations. So, as we know, PFAS is a big family. It's basically impossible to detect the forever chemicals one by one. So we have to think about the possibility to use some other tools. In terms of the environmental management, we can see there are actually different categories has the different priority. So at the current stage, PFOS and PFOA and their isomers basically are at the highest priority. So we can try to link other PFAS with priority PFAS. So this is the basic idea. At the same time, we also need to do some priority analysis in terms of those emission sources. Here, I just want to take the drinking water as one example. We can imagine, there are a lot of industrial emission sources, including from plating, firefighting, the PFAS production, for polymer production, or textile finishing industries. So whether or not the wastewater has been treated in the wastewater treatment plant, finally, these dirty chemicals still can find their way into the environmental media. So just a question of the time, finally, they will enter into the drinking water sources. And then this is the main reason why in our tap water, we can detect these chemicals. There are lots of data about the PFAS contamination in ambient environment, but we still have not so many data set about the emissions at the source, especially for the case of China. Still, we are working on this topic. We hope to clearly describe the existence of these chemicals in various industrial formulations. We believe that this is the right way in terms of the priority for the environmental management. This is a basic situation in China. I give a short list of those main industrial formulations. All these are currently in use. They are closely related to the PFAS as well as the release or the contamination. If we have no data about their occurrence in the industrial formulations, it means that we have no target for the environmental management. It means that no action at the government level. So we can have a look at these names. Class B foam normally we can say AFFF or FFP. Yes, these are the leading formulations we can find for firefighting, especially for the Class B fire accidents. The second category is textile finishing agents. China is one of the top producers on this point. Then the next one is chrome mist suppressant. We call it CMAs, used for the hard chrome plating or the decorative chrome plating. Also, we have the huge business. It's about the fluoropolymer production, such as the PTFE, PBDF, FEP, FKM, something like this. The PFOA and their substitutes have been used for the purpose. Because today's topic is about the fluoropolymer, so I just wanted to select two of these four categories. According to the information we received from the industry or from the industrial experts, we know that some side chain for polymer might be contained in the Class B foam surfactant or the textile finishing agents on the Chinese market. Now let's have a look at the strategy for the PFAS analysis. Here, I hope most of you know that we have the target analysis, we have the suspect screening and the non-targeted analysis. It's just like the iceberg. For the target analysis, we only focus on the visible part. Here I give some examples about those commonly used methods, standard methods. In China, in USA, also in other countries, there are many such standard methods of the target analysis. But we also are quite curious about those invisible parts, just like this. So for today's talk, I will talk about the precursors, especially using the top assay and its modification. Then we also have the total organic fluorine. It does not mean that we can describe the details of the iceberg, but we can give the rough scale of the PFAS contamination. Yes, the combustion ion chromatography for the NMR. These tools can be used for the purpose. Then we also can use, for example, the high resolution MS coupled to the LC to investigate the unknown PFAS without the adoption of any chemical standards. So for this purpose, we call the suspect screening on our target analysis. In my laboratory in recent years, we developed the comprehensive analytical methods, just according to the strategy here. In particularly, we also modified the current practice a bit. We developed two new methods. Basically, they are modified from the existing practices. One is called the top plus assay, and the other is called the TROF, the total reducible organic fluorine assay. I will introduce a bit here. Firstly, let's have a look at the comprehensive test protocol of the PFAS. Start from the sample preparation. Normally, we need to use, for example, methanol for as a solvent. Also use some SPE cartridge for the cleanup purpose. And then for the routine normal test, we use LC-MS for the direct test. Also, for the precursors, we can still use LC-MS, but the target changed into the precursors. We call it the total oxidizable precursors. Then we also can use the ion chromatography for the purpose of the total reducible organic fluorine. testing. Finally, we can establish a sort of the mass balance in terms of the fluorine. So this is the final purpose. Always we can find this big gap between the total consumption, total concentrations of the detected PFAS and the total organic fluorine. So in this case, we will use the Q-TOF, the high resolution analysis, to evaluate for the suspected screening and the non-targeted analysis. Normally, we can find a lot of the new structures in the industrial formulations. For today's talk, I will mainly talk about the TOP, total oxidizable precursor assay, as well as its modified version. We call it TOP Plus assay. Here is a comparison between the standard version and the modified version. We can have a look. For the standard version, basically it's based on the heat activated persulfate oxidation. You can see the temperature normally is 85 degrees, and we need 6 hours to complete the oxidation purpose, because we hope that we can oxidize precursors to convert them into the detectable PFCAs, those carboxylic acids. We like this idea, but we do not want to wait for so long time. So we decided to do something to shorten the required time. So finally, we find the solution. We use ultraviolet irradiation to activate the persulfate instead of the heating. Then in this case, we can shorten the required time period here from 6 hours to just 1 hour, but as always we can get quite comparable results for these modified version and the standard version. We have published this method in Science of the Total Environment. This is the mechanism of the standard TOP assay. We can see under the specified conditions, I mean, we're using persulfate at the fixed concentration. We also fix the temperature and we fix the pH value. Then in this case, we can ensure on this screen, reaction 1 and reaction 2, we can ensure that in the system, the main ROS is not the sulfate, but it should be the hydroxyl radical as the key ROS. Then in this case, we can expect on the right side, these conversion reaction can occur. For the ECF precursors, we can expect such a conversion into the PFOA, while for the fluoropolymer precursors, we can expect those short chain PFCA, those carboxylic acids, can be generated from the oxidation step. So this is the main mechanism. While for the modified version, basically the reaction is exactly the same. The only difference is that for the activation mechanism of the persulfate, we change from the heat into the ultraviolet radiation. So here is a comparison from the target analysis. We take the EPA method as one example, and then we have the TOP assay and we have the modified TOP assay. So we can see clearly the differences among these methods. Now let's have a look at the recovery comparison for the typical precursors, because it's well known that these are precursors of the PFCAs. So we use these chemicals to check what kind of intermediates have been generated from the oxidation step. So we can see at these lines for top assay or for the top plus assay, always we can see high recovery can be realized. So it looks nice. The other new method we have developed is an alternative method to the combustion ion chromatography. On this slide, you can see the basic mechanism. The idea is to use the ultraviolet light radiation together with sulfide. In such a system, if we control the dosage as well as the pH value carefully, we ensure that if the pH value is high enough, typically it should be higher than 11, then we can expect the main radical in the system is hydrated electron. Such electron is very strong reagent. It can attack all the PFAS in the system, and then we can expect the fluorine, organic fluorine can be reduced. Then we can see that inorganic fluoride ion will be generated in the system. After such a conversion, it's easy to detect. For example, we can use an iron chromatography for the purpose. So if such conversion is nearly complete, then we can use such a mechanism to get the exact concentration of the total organic fluorine. So this is the mechanism. Here, we don't need to use any combustion unit. So this is the reason we want to distinguish the results here. We call it the total reducible organic fluorine instead of the total organic fluorine. Okay. This method also has been published in the Journal of the Stockholm. The idea actually comes from our previous study, but it's not for the analytical method development purpose, but for the degradation, for destruction technology purposes. We have published on ESMT water research in chemical engineering journal or journal of hazardous materials. So if you have interest, you can check the original literatures. Now here just gives some information about the recovery and the calibration curve. So we can see for dosage at the 20, we can see if we can use 6 hours for the conversion, then we can expect that most of the organic fluorine can be converted into the inorganic fluoride. Then after 6 hours, we can take the samples. Here we use the normal iron chromatography to detect the concentration of the fluoride. That's it. So on the right side, we can see the calibration curve looks nice. Now, in today's talk, I will talk two case studies. One focuses on the AFFF surfactants. We all know that fluorinated foams are the current solutions, especially in many developing countries, including China, for the Class B fire. Class B foams, fluorinated and fluorine-free, but for the case of China, the F3 is not the current practice. For the family of fluorinated foams for Class B fire, we can see actually there are several main categories: HFF and AR-HFF, FP and AR-FP, and FFP and AR-FFP. So these are the leading formulations we can find on the market. We also know that for the situation in Australia or in European countries, ECA, and for example, Queensland has issued some sort of standard for the limits of some specific PFAS in the foam. Especially for the example of Queensland in Australia, we can see they clearly said that you can use top assay to detect the total fluorine from C7 to C14 to check the number. If your foam contains too high concentration of fluorine, then it's not allowed to be sold on the Australia in the Queensland market. Now let's have a look at the situation in China. China is the largest producer of chlorinated foams. We know about 40% for the domestic market, while the other 60% for the international market for the export purpose. For the domestic market, for many years, we are using the PFOS-based disinfectant. It's come from the ECF, electrochemical chlorination process. While for the export products, basically it's based on the polymer-based surfactants, normally imported from USA, especially for some leading companies like the Camus, like the Camgar and the Dynex. Here on this slide, I give the data in 2014 and 15. We can see the total production of such foam concentrate as well as the corresponding PFOS. Basically, these numbers are quite big. It's quite interesting to notice that after the international, detailed inventory survey, we can see, although we have hundreds of producers of the foams, but actually for the producer, for the vendors of those HFF surfactants, there are very few. 6 vendors, 6 producers of such HFF surfactants occupy most of the market share, especially for these 2, Shanghai Weitan and another company, BJCPC. These 2 companies, basically, we can see they are the main players in the market. Then after quite time-consuming negotiation with the industry, we finally get the agreement and cooperation of the co-producer of HFF surfactants, it's Shanghai Weitan. They provided us all their formulations of the HFF surfactants. Also, they clearly told us that they have these 2 products, 61169 and 6116. These 2 formulations contain brominated copolymer. So this is quite interesting. We then use the direct test, I mean, just use the LC-MS for the routine target measurement. And then we also use the standard practice of the TOP assay for the precursor measurement. We can see before and after the oxidation, the detected concentrations significantly increased. On the left side, we can see it's the normal number. The numbers are here. This is the original number. And then on the right side here, after the oxidation, then we can see the numbers significantly increased. This is for the PFOS-based products, comes from the electrochemical chlorination processes. Similar situation we can find for the polymer-based products. On the left side, the numbers are here. On the right side, these are the numbers after the top oxidation. So always we can see the numbers significantly increased. Then we also can have a look at the comparison if we also include plus the modified version of copper assay, then we can see these samples containing the four polymers. The normal test, the number is the lowest, while for the numbers from the top assay and the top plus assay, yeah, they are significantly higher. And also, we can notice that for the numbers from the top assay and the top plus assay, basically they are very similar. They are very, they are quite comparable. So this is the situation. Here is a summary. We can see for these four formulations containing the polymers, the normal test, basically we can detect very little. Then the top assay, yeah, we can see significant increase. While for the top plus assay, yeah, we change from the heat activation to the UV radiation activation. Then we can see we get a much higher concentration. Also, these numbers are quite comparable. So this is the first case study. And the other case study we want to talk is the textile finishing agent. China is also a top producer here for the textile products. We can see textile finishing agents directly purchased here from the Chinese market. We can here is the sample list. We want to make a comparison here for the samples collected from a different year. So we can see 2013 and 2017. Then we follow the quite similar methodology. Firstly, I want to highlight that nearly zero PFCAs have found in the normal test using LC-MS without oxidation. Then we believe that the LC-MS is not the right choice for the analysis of PFAS in the textile finishing agents. We suppose that there should be high concentration of TOH. So we introduced the other two, GCMS, for the purpose. On this slide, we can see this is total concentration. Yeah, we can see on the left side, it's a polymer-based PFAS. The main concentration comes from the FTOH instead of the PFCA or PFSAs. On the right side, we can see it's ECF-based TFAs. The situation here on the left side and the right side are quite different. Then we can have a look at the situation here after the oxidation. I mean, if we use the proper assay, then we can see significant increase of PFCs after the oxidation. The numbers are just for the change, delta concentrations of the specific PFCs. Always we can see the numbers significantly increase for different lengths of the carbon chain. It's quite interesting. When 2 years ago, we wanted to revisit the situation on the Chinese market. We collected a new sample set. These are the trade names of those products we collected from the market. You can see, especially for the Japanese ducking, yes, this is the leading vendor here in Chinese market. Then we can have a look at the right side. This is the results. It's quite reasonable to see that if we use a normal test use a direct test based on the LCMS, we can find nothing, nearly zero. But if we introduce the top assay, yeah, we use the heat oxidation. We use the heat to activate the sulfate for the oxidation purpose. Then we can see high concentrations of PFCs can be detected. So this means that in this case, we can believe that top assay can be a good tool to reflect the existence of PFCA precursors in the samples of the TFAs. Also, we at the beginning of my talk, I mentioned the other method we have developed is total reducible organic fluorine. Then if we put the three numbers together, I mean the concentration we directed from the direct analysis, and then the number we got from the top assay analysis, and also we put the detected concentration from the TR8. Then we can see always we can find the big gaps in terms of the fluorine mass balance. This gives us a strong reason we need to use some advanced technology, especially like the high resolution images, Q-TOF images, to investigate in details what kinds of unknown structures are in our samples. Yeah, on the right side you can see the samples, yeah, and its corresponding vendors. The whole story, yeah, you can find in our publication, yeah, in the Journal of Stockholm. Here, we also want to link our study with a recent PSMT paper. This is this study, yeah, focused on the coating. We can see for the school uniforms. On the right side, this is the key message. Before the oxidation and after the oxidation, we can see using TOP assay, we can find significant increase of the detected concentration of PFAS. This is exactly compatible with what we have found in our studies. So finally, I want to make some conclusions. Firstly, we can see normal tests using LCMS is not effective for industrial formulations containing fluoropolymers. Significant increase of PFCs can be found when using top assay or the modified version of plus assay for such samples. Yeah, we have showed the example, two case studies, one for HOF surfactants and the other for the textile finishing agents. Both, yeah, can support the statements above. The second conclusion is the results from top plus assay are quite compatible with the standard top assay method. Thirdly, we can see suspect screening and non-target analysis are necessary for a mass balance of the fluorine. Here, I just want to give one example here about what we have done. We published in the Journal of Environmental International. This is one example focused on the HOF surfactants. We use the high resolution Q-TOF images to investigate these fluoropolymer containing surfactants, and then we find some unknown structures. Yes, these are quite interesting results. Hope some of you can download from the URL here and then read the story. Finally, I want to say for the investigation needed, especially we hope that with the cooperation and the information input from the producers, because currently many related formulations have been regarded as CBI, the confidential business information. This is not so good. Yeah, there should be some communication mechanisms between the academic society and the industrial society. Then in this case, we can ensure that we are always together on the right way for a sustainable development future. Okay, yeah, Dr. Weber, yeah, this is my presentation. Thanks very much.
Yeah, thank you very much, Professor Huang. Very interesting, very good presentation. Question. So you have also shown the total fluorine, and you had studied these polymers from firefighting foams and also for the textiles. Did you do for some of these products also a total fluorine assessment? When you, yeah?
Yeah, here. Here, actually, this is the answer. You can see on this slide, yeah, we have the numbers for the total organic fluorine here. Yeah, 2 samples are actually textile finishing agents. Yeah, you can see on the right side, these are the textile finishing agents. So always we can see the total organic fluorines are much higher than what we can quantify from the direct analysis or from the TOP assay analysis.
Yeah. What compounds, what fluorinated compounds do you suspect are these, let's say, missing organofluorines?
I believe, yes, they are copolymer, fluorinated copolymer. Yeah. Also, yes, most of them should be the side chain polymers. If we think about the mechanism of the textile finishing agents, most of the products are based on the polymerization formulations. So, yeah, it's exactly your topic today. Side chain, fluorinated copolymer. Yeah, these should be the reason for the for the big gap. For the oxidation, yeah, or some other approaches might work, yeah, for the destruction of such polymer. Then in this case, we can expect the generation of some small molecules. Then they can be the target for the LC-MS analysis. So this, yeah. So this is actually what we are working on now. I hope in the future I can find a proper chance to to share our new findings.
Yeah. This means that also your, let's say, top plus assay is not, let's say, sufficient to degrade most of the side chain fluorinated polymers in your opinion.
Yeah, it's hard to say according to the current data. Yeah, we can have a look at this slide. We can see that although these 2 data sets are quite comparable, but still we can see always the detected concentration from the whole class is slightly higher than that from the standard top assay. So in this case, we can suspect that maybe the top class is a bit stronger than the normal top assay.
Yeah.
But we still need more experiments to check whether or not it's strong enough to destroy the copolymer.
Yeah. And I mean, one question is also if such assays might degrade P4 itself. Have you one time checked if when you...
Yeah, actually, this is a very important aspect. We have conducted comprehensive studies just to ensure that PFCs are the endpoints for the conversion. The reason, reason is very how to say interesting. The key issue is the pH value. If we reduce the pH value, then the mechanism will be changed. then in this case, the endpoints will also be changed. So pH value, at as high as 11. This is very, very important. 11 or 12. Otherwise, the hydroxyl radical cannot be the leading radicals in the system. Then the mechanism, the original presumption will be destroyed.
Okay.
Okay.
Thanks much. Good luck for progressing your top essays towards, let's say, a complete degradation of the side chain fluorinated polymers. We are looking forward to it.
Thanks very much.
So now we come to the last two presentations. So they are both from Dr. Nudjarin Ramungul. She is senior researcher at the National Metal and Material Technology Center, MTEC, in Thailand. At the moment, she's traveling from Thailand to Australia, so therefore she has recorded her presentations, and her presentation topics are two methodologies where we do not need extraction of the polymer. So you have heard from Dr. Gruber about the challenges of extraction and cleanup. So here now we thought at the end we show two presentations where you do not need an extraction, but still you get information about the chemicals in plastics. And the first presentation is screening of brominated flame retardants in electronic waste plastic without extraction by Fourier transfer infrared spectroscopy. So please, Lisa, we can play. Yes.
Hello everyone, my name is Nudjarin Ramungul from National Metals and Material Technology Center, or MTEC. Today I would like to introduce two screening methods. The first method utilizes the FTIR for identification of brominated flame retardants, or BFR, which will be presented shortly. The second method involves the use of PYTD GCMS for the identification of plasticizers in soft plastics. Before I begin, I would like to express my gratitude to Dr. Roland Webers and the organizers at the IPCP for extending an invitation to present our work. It is our pleasure to share our research with you. Unfortunately, I am unable to present our work in real time today due to scheduling conflicts. Thank you all for your attention. As you may aware, detecting and monitoring POP BFR poses significant challenge. Several factors contribute to this challenge. Firstly, it is important to note that there are many types of BFR, and these substances have been used in a wide range of products. At the present, Annex A of Stockholm Convention includes 5 BFR, and it is anticipated that more to come. Consequently, the detection and monitoring of all POP BFRs across all relevant products categories would be a formidable challenge. In addition, there is a severe lack of upstream data available from products producers and national database. Analyzing BFR at the downstream stage is highly costly due to intricate test method involved. These high analysis costs act as significant barriers impeding comprehensive studies and testing on BFR. Consequently, these limitations have resulted in a scarcity of tests and studies conducted on BFRs. Insufficient data availabilities hinders our abilities to predict flame retardants usage patterns accurately. Furthermore, the lack of comprehensive data also restricts our capacities to make informed decisions. Insufficient information on BFR undermines our abilities to develop appropriate policies and regulations to effectively address the associated risks. In our assessment, we aim to explore whether the ATR-FTIR can help bridge the information gap. ATR-FTIR spectroscopy is a promising technique due to its abilities to provide valuable insight into a composition of the materials. It enables the identification of existing functional groups within samples, offering rapid results with minimal samples preparation requirements. This efficiency not only reduce analysis time, but also minimize associated costs, making ATR-FTIR an excellent candidate for BFR detections. Furthermore, FTIR spectrometers are readily available in many laboratories, making this technique accessible to researchers, regulators, and industrial professionals. This slide represents examples of ATR-FTIR spectra obtained from actual samples. The spectra clearly demonstrated that different BFRs display unique patterns. However, it is important to note that interpreting FTIR spectra in real-life samples can be challenging. This is because spectra obtained from real samples are often a mixture of multiple components, including pigments, stabilizers, fillers, and more, leading to spectral overlaps. Many WEEE samples are commonly black in colors, which absorb significant amounts of energy from infrared light. Also, it is important to consider that recycled pellets, particularly those that have undergone multiple heating cycles, may contain degraded resin. This degradation can lead to change in chemical composition of materials and result in spectra that are distorted or altered. The use of ATR-FTIR for identification of BFR in WEEE plastic has several limitations that should be taken into consideration. This includes zero overlaps, spectral overlaps, limited sensitivities for trace amount, lack of specificity for specific BFRs, and challenge in identifying novel substance and lack of quantitative accuracies. In our research, we propose the use of machine learning or ML, which is a branch of AI, to aid in analysis of ATR spectra of WEEE plastics for the classification of BFRs. ML techniques have proven to be effective in clustering spectra based on their most distinguishing features. In these studies, we identify relevant features that contribute to classifications, including both material-related, testing-related factors. By addressing unwanted variations and ensuring that spectra are reproducible, the algorithms are capable of grouping materials with similar additives together. By employing ML algorithm, we aim to enhance the accuracies and efficiencies of BFR classification in WEEE plastics. This slide demonstrates the outcome of grouping or clustering of different datasets, after removing unintended features. It showcases a PCA score plots and associated cluster plot, which in these figures are shown in unique colors. As you can see, the dataset were ATR-FTIR spectra obtained from more than 500 real samples and 53 impute spectra derived from homemade materials. Upon conducting further analysis using more accurate techniques such as GCMS, we found that samples belong to different clusters actually contain distinct type of BFRs. Please note that in our case, we have to incorporate impute spectra obtained from homemade materials into our dataset. This decision was made due to the rarities of samples containing the target BFR, which is the PBDE in VABS materials. It is unfortunate that we were unable to acquire a sufficient number of real samples containing PBDE during the course of our studies. This is our proposed model framework, which we have named it a multi-stage semi-supervised learning or SSL framework for the identification of BFR in EUS plastics. The framework commences with a materials dataset comprising a data obtained from ATR, FTIR, and EDXIF techniques. Within this framework, we have developed two semi-supervised machine learning models, the resin identification models and the BFR identification models. The semi-supervised natures of the frameworks arise from the utilization of a combination of supervised and unsupervised modeling techniques. The unsupervised components involve clustering that you have seen. We cluster the materials into distinct groups. This clustering process does not rely on labels data, but rather groups similar materials together based on their intrinsic properties. The supervised components involve a detailed analysis of materials and expert analysis of ATIR data, resulting in the labelings of representative materials from each cluster. This slide provides a detailed process flow for models development. However, due to time constraint, we will skip this slide for now. You can review it later on when you have time. This slide provides a more detailed explanation of the SSL1 or the resin identification models. The process begins with data cleansing and pre-processing of data to ensure that the data are aligned and normalized. This will enable us to have consistency and comparabilities of the data. Following the processing step, random sampling is performed from the dataset to create a training dataset. These random samplings ensure representative subsets of data for model development. Next, clustering is conducted based on the first dominant components, which is, in this case, the resin type. The clustering algorithm groups similar samples together based on their resin types. From each cluster, a manual labeling process is performed, where samples are carefully identified and labeled. After the labeling stage, the k-nearest neighbors or KNN algorithm is employed. In our case, we use k = 5 for samples classification. The KNN algorithm utilizes the labeled samples to classify new samples based on their similarities to the labeled samples. In our case, we have 7 types of WEEE plastics, namely ABS, PS, PP, PC, PBC, PB, and PPO. However, for the purpose of the BFR identification, we have selected only ABS and HIPS materials for classification, for classified resin type for further modeling. These two resin types have been chosen based on their relevance and their potentially associated with our targeted BFR. Next, the modeling process for the SSL2 or BFR identification models It is indeed similar to the SSL1. However, there is a difference in the approach due to variations in the BFR usage pattern. In this case, we have developed specific models for BFR identifications for each resin type, focusing on ABS and HIPS. The rationale behind this lies in the fact that we found that BFR usage pattern will indeed varies across different resin types. Therefore, developing resin-specific models allow us to capture the distinct characteristics and variations associated with BFR and ABS HIPS, associated with BFR in ABS and HIPS materials. By creating separate models for each resin, I think we can enhance the accuracy and specificities of the BFR identified within the respective resin types. The types of BFR included in our models is summarized in this table. These are based on the types of BFR typically found in our dataset. For the cross-validations, these figures illustrate the cross-validation results for BFR in ABS trainings. As shown, the model performed optimally with K values below 8. But for our initial attempt, we have chosen K equal to 5 to strike balance between avoiding overfittings and being cautious due to limited data and a limited number of test results available for model development. Finally, we use our models to aid the identification of BFR and ABS. Through this analysis, we have observed distinct pattern of BFR usage in ABS materials extracted from end-of-life PC monitors in Thailand. It is noteworthy that the BFR employed in these materials were not PBDE, but rather BTBPE, followed by a transition to TBBPA later around in the year 2000. Interestingly, around the year 2005 or 2006, there was a significant decline in the presence of CRT monitors and a subsequent phase-out of BFR altogether. This coincides with the enforcement of EU RoHS directive. In summary, our study has showcased the effectiveness of utilizing ATR FTAR in conjunction with ML classification algorithm for the identification of BFR in WEEE plastics. The proposed method provides meaningful information for understanding the usage pattern of BFRs in Thai WEEE plastics. It can be useful for various applications such as checking feedstocks, improving products, and developing data to inform decision makers. The method, though, is complementary to existing highly sensitive analysis. Thank you very much for your attention.
Yes, thank you, Nudjarin. A very useful tool. I have discussed with Nudjarin, and she said that normally she thinks that the PBDEs need to be in a single pellet in the low percent range, that we can see it with FTIR. This could be especially interesting when there are shredded samples, and Nudjarin is analyzing here in shredded samples individual shreds to find out how much percent is especially impacted. And if this is automated, it could be a quite interesting tool to evaluate shreds for not only the average impact of PBD, which we can do with extraction measurements, but to understand how much or what share of electronics contain the PBDEs at high levels. Coming to the last presentation, again from Dr. Nudjarin Ramungul. So this is on screening of short-chain chlorinated paraffins and medium-chain chlorinated paraffins and other plasticizer in PVC without extraction and cleanup by pyrolysis GCMS.
Hello everyone, it's me, Nudjarin Ramungul from MTEC again. In this presentation, I would like to introduce the screening of SCCP and MCCPs and others plasticizers in PVC products without extraction or cleanup by pyrolysis GCMS. This method aims to detect and analyze short-chain and medium-chain chlorinated paraffin and other plasticizers in soft PVC products without the need for extraction and cleanup steps. Instead, it utilizes pyrolysis gas chromatography mass spectrometry or GCMS for screening purpose. Pyrolysis GCMS is a technique that involves heating of samples to relatively high temperatures in inert atmosphere, causing it to decompose into small fragments. These fragments are then separated and identified using gas chromatography coupled with mass spectrometry. By employing these techniques, we can bypass the traditional extraction and cleanup procedures, which often require time and resources. As we know, flexible PVC heavily relies on the use of plasticizers, some of which have been globally banned due to concerns regarding health and the environment. However, the understanding of the plasticizer usage pattern in soft PVC products in Thailand remains extremely limited, particularly due to the complexities involved and the associated high cost of material testings. In our extensive literature search, we did not come across any published studies that investigated the presence of short-chain and medium-chain chlorinated paraffin in Thai flexible PVC products. Moreover, there is a significant lack of studies examining the usage of non-targeted plasticizers in this context. A commonly employed test method, pyrolysis or thermal desorption gas chromatography mass spectrometry or PYTD GCMS, has been utilized in the IEC standards for assessing phthalate esters or PAEs in polymers. However, the IEC method was specifically validated for the analysis of trace amount of selected PAE in polymers. Our objective is to expand the capacity of this method to enable the simultaneous evaluation of the other compounds, including chlorinated paraffins or CPs and non-PAE alternative at realistic concentration levels. By addressing these research gaps, we aim to enhance our understanding of plasticizers usage in flexible PVC products, particularly in the context of Thai market. Furthermore, extending the PYTD GCMS method to include CPs and non-PAE alternatives will allow for comprehensive analysis, providing valuable insight into the composition of plasticizers in soft PVC products. Plasticizers can be classified into two main types: primary and secondary plasticizers. Primary plasticizers are the key substance responsible for providing the desired physical properties of the materials without causing compatibility issues. There are various families of primary plasticizers, with one of the most commonly known being ortho-phthalate ester or PAEs. PAEs can be further categorized based on their molecular weight, distinguishing between those with low molecular weight or low MW and those with high molecular weight. There are non-phthalate plasticizers available, such as adipate esters, terephthalate esters, cyclohexanoate esters, and more. Secondary plasticizers, on the other hand, are used in addition to primary plasticizers to reduce costs and/or to improve fire resistance. They are less compatible with the base polymers and can exude out under normal conditions. Chlorinated paraffins constitute the key families of secondary plasticizers. In the past, a commonly utilized combination involved the use of low molecular weight phthalate esters, such as DEHP, in conjunction with SCCPs. However, SCCPs were included in Annex A of the Stockholm Convention in 2017 due to their adverse health and environmental impact. Additionally, zero low molecular weight phthalate esters have come under regulatory control, particularly through the EU REACH regulation. Also, BBP, DBP, DHP, and DIBP, for instance, have been banned in the EU and in numerous countries worldwide. Flexible PVC can indeed be recycled. This slide aims to illustrate the relatively high buyback price of end-of-life soft PVC products in Thailand when compared to other scrap materials like PET bottles. It is worth noting that end-of-life flexible PVC products are also expensive, more expensive than end-of-life rigid PVC products, which lead us to the observation that focus on recycling soft PVC products may not necessarily be the PVC material itself. Our assessment method, the assessment method we employed was adapted from IEC 62321-8, published in 2017, which is a test standard specifically designed for analyzing phthalate esters or PAEs in polymers. By utilizing this method, we are unable to directly analyze samples without the requirements for extraction or purification steps. This streamlined approach offers several benefits, including time and cost saving, reduced risk of sample contamination or loss, and the ability to simultaneously screen for multiple constituents in the same samples. This slide showcases a schematic diagram of the PYTD TCMS setup utilized in our studies, along with the illustration of flexible PVC samples that were analyzed. The diagram visually represents the configuration and components of PYTD TCMS systems employed in our studies. In our studies, the soft PVC samples comprise the following categories: PVC boots, N equals 35 boots, PVC sheet from wires and cables, 56 samples, PVC or probably known as vinyl flooring sheets, 24 samples, and PVC garden hoses for 38 samples. It is important to note that local recycling practice often involves separating PVC boots into sole and ankle supports due to their varying flexibilities, which correspond to different plasticizers contents. Consequently, samples obtained as whole boots will further define into their corresponding soles and ankle support part for testing purpose. For the measuring conditions, we adapt from the IEC 62321-8. This slide provides a summary of the measurement conditions utilized in our study. Notably, the main difference lies in the use of high split ratios and the adjustment of the detection voltage. These modifications were necessary to accommodate high concentrations of plasticizers commonly encountered in real samples. However, it is important to acknowledge that this modification may result in reduced sensitivities. This trade-off between sensitivities and the versatilities of our PYTD TCMS method is a necessary consideration in our analysis. We have estimated that the limit of detection, or LOD, for our method is approximately 1%. This slide presents total ion current chromatogram, or TIC, obtained from reference plasticized PVC samples using PYTD TCMS in sim mode. Each reference sample consists of 30% designated plasticizers and 70% virgin PVC resin. The chromatogram shown here are overlaid without normalization. From the chromatogram, it is evident that different plasticizers exhibit varying response rate. Specifically, DINP and DIDP, which are mixtures of branches isomers, display lowest response and intensities in the chromatogram. However, despite this difference in intensities, The GCMS characteristic of the INP and the IDP, including their retention time and at least two identifying ion mass, or MC, are distinct enough to differentiate them from other plasticizers analyzed within these studies. These chromatographies represent the analysis of reference samples containing a binary mixture of MCCP and DHP and MCCP and DIDP in PVC, which are prepared in our laboratories. The objective was to determine if we could simultaneously analyze chlorinated paraffin and other primary plasticizers, specifically DHP and DINP. Upon examination on the left figures, it is evident that there are distinct patterns for MCCP and DHP. MCCP exhibits a characteristic wavy and undulating response, while DHP shows sharp and distinct peaks. Therefore, distinguishing between MCCP and DHP does not pose any challenge. However, the combination of MCCP and DINP could potentially be more problematic. Nonetheless, as demonstrated in the chromatogram, DINP exhibit a narrow clusters of multiple isomeric congener peaks. By examining the response in the DINP M to C ratios shown in the inset, it is clearly distinguishable from CPs. Overall, these findings indicate that while analyzing combination of MCCPs and DINP may present some challenge, it is still feasible to differentiate between them. These tables summarize targeted compounds and their MS characteristics under these studies. This slide presents an example of the results obtained from testing PVC booths using PYTD CMS in comparison to the solvent extraction method, which was used as the reference method and performed at a frequencies of 20%. The analysis demonstrated that all plasticizers identified using PYTD TCMS method were also identifiables using solvent extraction TCMS method, with a particular focus on the detection of chlorinated paraffins. Additionally, the results indicated the possible presence of a mixture of short chain and medium chain paraffins in the test samples. However, it is important to note that at the present, reliable differentiation between SCCP and NCCP has not been achieved in our lab. Further advancements are required to effectively separate and distinguish these two types of chlorinated paraffin. Overall, these findings highlight the comparabilities of results between the PYTD TCMS method and the solvent extraction TCMS method, while also acknowledging the current limitation in differentiating between SCCP and MCCP in the analyzed PVC samples. For the result summaries, while it is true that our method has limitation in detecting specific substance at low concentrations, resulting in some false negative, this trade-off was necessary to facilitate the simultaneous screening of all targeted plasticizers. Despite this limitation, the overall accuracy of 90% is quite satisfactory. Upon closer examination, we observed that our method is less sensitive to detecting DOA and DOTM compared to other plasticizers. This variation in sensitivities highlights the specific characteristics and challenges associated with different plasticizers compounds. Interestingly, although this method has not yet achieved the capabilities to differentiating between short chain and medium chain chlorinated paraffin, it demonstrates high accuracies in detecting chlorinated paraffin as a whole in real samples. This indicates that our method effectively captures the presence of CPs despite the current limitation in differentiating between the specific CP types. Overall, while there are certain limitations and variations in sensitivities across different plasticizers, the accuracies achieved by our method particularly in detecting CPs, is promising and contribute to the overall reliability of our screening approach. This slide shows the key findings of the results obtained by simultaneously identifying all targeted plasticizers in the 4 samples group shows very interesting findings. Overall, DHP, CPs, and DINP are the top 3 most popular plasticizers with frequencies of detection or FOD of 81%, 65%, and 61% respectively. The pattern of plasticizers found appear to differ across the different product groups. For PVC boots, DHP is the main plasticizer found in this products group with 93% FOD, followed by DINP, 65.1 FOD. Compared to other 3 products groups, CP are the least often detected in vinyl boots with only 30.2% FOD. Other non-PAE, for example, DHT, TOTM, DOA, are also found but at moderate frequencies, 20 to 30%. DINP, although we found it at quite high FOD, they never found alone, but is detected in combination with other plasticizers, especially DEHP. It should be noted here that DHP is a restricted plasticizers, while DINP is not yet a restricted plasticizers if they are not used for children. For cable sheet, comparing with our other 3 product groups, DHP appear to be the primary practice. For all other 3 products group, DHP appear to be the primary plasticizer used, with CPs as secondary plasticizers. But for cable sheet, however, it appears that DHP has been replaced by DINP with close to 80% FOD, while the FOD of CP as secondary plasticizers remain also high at 78.6%. DHT, which is the telephthalate part of the DEHP, and TOTM are also detected but at lower frequencies, only 15 to 20%, and surprisingly, mostly mixed with DHP. DHT and TOTM are supposed to be the alternative to DHP, which is forbidden, which has been banned by many regulations, including the ROS directive. It is to our surprise to find the restricted and non-restricted plasticizers together in one samples. Nevertheless, when compared with other products group, the detection rate of DHT and TOTM in wire and cable sheets are relatively high. The IDP, which is a popular alternative in Europe, is also found, albeit at very low FOD, only 5%. As it can be seen here, although Thailand has not yet enforced domestic control similar to EU ROS directive, this type of patterns may indicate the influence of EU ROS directive in Thai electrical and electronic equipment. For vinyl flooring sheets and mats, all vinyl flooring samples tested contain DHP. Most of them also contain CPs at quite relatively high rate of 65, close to 65% FOD, and DINP at 70% FOD. BBP, which is the only polar plasticizers in these studies, is found only in this application group. Interestingly, samples with BBP do not contain CPs, but rather are blended with DHP or DINP. Compared with other 3 products groups, the number of plasticizers found in this group is lower, only 6 substances. Nonetheless, about 67% of these sample tests contain more than 2 plasticizers. Close to 63% of these contain the main trios, DHP, DINP, and CPs, with and without the 4th plasticizers, mostly DHT. The plasticizers found in garden hose are predominantly the binary DHP and CP blends at close to 70% FOD. The FOD for DHP is also very high, almost 100%. We have only 2 out of the 38 total samples without, there are only 2 samples without DHP. Compared with the other 3 product groups, the FOD for non-restricted PAEs and non-PAEs is very low, and all samples also contain restricted PAEs. About 16% of samples also contain DINP, all of which are mixed with DHP, and half also mixed with CPs, and surprisingly, DIDP and TOTM. For the key findings, there's another way to look at the results. With this slide, we show the numbers of plasticizers found within the same samples. Vinyl booths are similar as seen in the previous slides. Vinyl booths are highly plasticized. Most samples, close to 60%, contain 3 or more plasticizers, with one samples contain as many as 7 plasticizers. Remarkably, the restricted DHP and the yet unrestricted DINP are frequently found together at 60%. Among these, 23% were binaries DHP and DINP, while the majorities were the combination of other plasticizers, namely DHT, TOTM, CP, DOA, and DBPs. As for the cable sheet, as shown in the figures, cable sheet mostly comprise 2 or more plasticizers at 91%. There are only 5 samples that contain singular plasticizers. The most frequently found combination are the binary DINP, not the EHP, and CPs at about 35%, followed by the tertiaries DINP, DHP, and CP blends at about 18%. Mixing of restricted and non-restricted plasticizers is also found in this application, but at a lower extent, possibly due to the influence of the ROS directive. Among the 43 samples with DINP, about 46.5% are found with CPs and non-restricted PAEs, and 54% are blended with CP and restricted PAEs. As for the garden hose, plasticizers used in the garden hose are less complex compared to those of other products group. Most of them are binary system, of which most were DHP and CP. Though limited, samples with more than 2 plasticizers are also found contain DHP and CPs. This may be because most of the samples in these studies are clear hoses, which are less likely to contain post-consumer recycled feedstocks. Only 1 clear hose samples contain binary DEHP and DINP. All samples found with DINP and DIDP are colors and opaque hoses. In conclusions, we have demonstrated that PYTD GCMS can be used to simultaneously screen PAEs, PAE alternative, and CPs in soft PVC products. The method is fast and economical, hence allow us to cover sufficiently large number of samples to reveal plasticizers' usage patterns. This study showed the widespread intermixing of several plasticizers, restricted and non-restricted, in the selected products group that can come into close and prolonged contact with users. Since there is no obvious incentive for producers to intentionally apply many types of plasticizers into each individual product, this intermixing can be attributed to uncontrolled open-loop recycling. In order to transition toward a circular economy safely, the risk associated with this indirect recycling of plasticizers to be managed, preferably from the design stage or the upstream of the product first life. The information presented here is based on the findings published in the GEEA journals. For more detailed information and comprehensive understanding of the studies, I recommend referring to the papers. These papers will provide in-depth insight, methodologies, results, and analysis related to the research conducted. Thank you for your attention. Bye-bye.
Yeah, thank you very much for this very interesting presentation. Very useful, considering that short and medium chain chlorinated paraffins are produced in about 1 million tons per year. Short chain are already listed as POP. The medium chain are evaluated for POP. And this method had 100% finding if they were present. This means no false negative. So in addition, Nudjarin said, yes, this method cannot quantify, kind of only semi-quantify chlorinated paraffins. Tomorrow we will have the last day of our workshop, which includes the instrumental analysis. There we will have 2 presentations on a quantification of short and medium chain chlorinated paraffins, where you can learn that. Then one other comment to the presentation. Nudjarin mentioned chlorinated paraffins are secondary plasticizer for PVC. Yes, in most cases they are secondary plasticizers, but there is one study in China where they have found that chlorinated paraffins are partly present in PVC in concentrations of 30 and 40%. So this means that in some cases for PVC they are even used as a primary plasticizer. There was one question in the chat about if there is a link to the UNEP project or program for developing countries. I have shared here the link to the global monitoring plan of UNEP. To this project I mentioned. This means the next phase of global monitoring plan. There is not a real link or website. This is just at the moment under development. And here governments which are part of the Stockholm Convention, developing countries can contact UNEP Geneva and see if they are already a part of the study, and if not, they can communicate with UNEP and see if they can become part of the study in future. I do not see further questions, so therefore from my side that's everything. Only the recommendation for participating for tomorrow. Anna, would you like to close today's webinar? Yes.
Sure, thank you. Thanks, Roland, and thank you to all the presenters for very informative and rich information. And we will be sure to post the recordings as soon as we can on the IPCP website, and following that with PDFs of the PowerPoints that we receive. So I posted the link to the website in the chat, and if you are not registered for tomorrow, be sure to register, and you can still invite others to do the same. So thank you again.